A Raptor Works production.
I bet you remember when you first got your Falcon 9. And wow, that was great. It was so clean and so nice, and that made you really happy. But these days, it's looking a little old. And all your friends are talking about Starship and Raptor, and you're wondering if your Falcon 9 is kind of past its prime. Well, I don't think so. I think you should Raptor your Falcon 9. Now, what would that mean? Well, let's look at the two engines we're comparing. We have the Merlin that comes default. It's a stock engine for the Falcon 9. And we have this new Raptor. So, the Merlin, it's a gas generator Kerolox engine. So it's burning RP1 and liquid oxygen. And the Raptor, well, it's a Methalox engine. It's burning liquid methane and liquid oxygen. And it's a full flow stage combustion engine. The thrust, Merlin, about 850 kilonewtons. Raptor, 1810 kilonewtons. Maybe going higher. Turbopumps, Merlin has a single. Raptor has double turbopumps. And the boost pressure, Merlin runs its combustion chamber at about 1410 psi. Raptor all the way up at 4000 psi. And finally, ISP. Merlin runs 282 at sea level, about 311 in vacuum. Raptor, 330 sea level, 348 in vacuum. Raptor is one spicy unit. But it sounds like that'd be pretty hard to do, you know, taking the Merlins off and putting the Raptors on. But Raptor Works makes it easy. We can give you everything you need. We make the Raptor adapter. That lets you take a Raptor and put it where your Merlin would go. We can give you the MN1 flight computer from Dr. Rocket. And that will replace the existing flight computer and do exactly what you want. And finally, we give you a detailed 15-page instruction booklet that'll tell you everything you need to do. Once you've done the engine swap, we give you this nice decal that you can put on your Falcon 9, and this will show everybody that your Falcon 9 is now Raptor powered. And finally, you get a 3-issue free subscription to Raptor Fan magazine. So let's dive in a little deeper about what this would take. We're going to need to do some fuel system modifications. And then we're obviously going to need to do some engine bay modifications. So for the fuel system, as you probably know, your Falcon 9 at the bottom, it has a tank for RP1. And at the top, it has a tank for liquid oxygen. Now it turns out, because we're switching fuels, the RP1 is a lot denser than the liquid methane we're switching to. So we're going to have to change our tank size a little bit. But that's pretty simple to do. All you need to do is, near the bottom of the LOX tank, we're going to draw 2 lines about 2.6 meters apart. Then we're going to cut the tank at those lines, take that section of tank and set it aside. Now, near the top of the RP1 tank, we're going to draw another line, cut that, move that piece over on top of the piece that came from the LOX tank. Weld that together. Now take the leftover RP1 tank and the leftover LOX tank, and we'll weld those together. And then we'll end up with tanks that work for liquid methane and for liquid oxygen. So they'll be just the right size for us to run the Raptor. Next, we're going to have to make some engine bay modifications. this is what the bottom of the Falcon 9 looks like with the 9 Raptor engines. I mean the 9 Merlin engines. So, we could just replace those with Raptors. But that has a little problem. They actually just don't fit. So, what are we going to do? Well, I'm going to go find our techs. I'm going to pull out all of those engines. We're only going to put 4 Raptors back. Now, they look like they kind of fit, but you notice they hang out over the side. So we can just scoosh them in a little bit. The Raptor adapter will do that for you. And then we have our final setup. So what sort of performance can we expect with this sort of setup? Well, let's go look at that. Going to start by looking at delta V. I'm sure you all know about delta V. Say it with me. Delta V is equal to the ISP times 9.8 times the natural log of the mass ratio. What does that mean for these two engines? Well, for the Merlin, 297. 297 is the average ISP. So, ISP average between sea level and vacuum. And 3.64, that's the mass ratio. We plug that in, and what do we get? We get about 3,755 meters per second of delta V. Let's look at Raptor. 339 is the average ISP. Multiply that times 9.8 and times the natural log of 3.13. What do we get? 3,787 meters per second. Raptor wins. Now let's look at the other thing we care about. Thrust to weight. So Merlin and Raptor, the thrust to weight at takeoff of the full stack. And this is if you're launching a full stack, full payload of Starlink satellites. 1.36. Raptor, 1.48. Raptor wins. So that gives you about 10%, about 100 meters per second less gravity losses. And that translates directly to more payload. So I recommend you look at our Raptor Works kit. It's exactly what you want to Raptor your Falcon 9. Okay, so let's actually look at the details behind this rather than the sales pitch. So when we look at the tanks, we're starting with that stock setup. And the problem we have is that the liquid methane is much less dense. So I'll show you how we figured out, or how I figured out, how big that tank would be. So we have the LOX, we have the RP1, it's Keralox. It's called Keralox because RP1 LOX would sound really stupid. We know how much there is in the stage, and we know what the mixture ratio is for the Merlin engine. So what that means is for every 2.6 kilograms of LOX, we have 1 kilogram of RP1. So based on that, I can figure out how much weight the propellant is in each of these. Then I can go look up the temperature of each of the propellants. Now the LOX is sub-chilled, which means it's colder than it would normally be, colder than it normally needs to be liquid. It's at about 60 degrees Kelvin. The RP1 is also technically sub-chilled, but RP1, when you cool it, kind of turns mushy, and it's not very good for turbopumps. So it's only chilled just a few degrees. So this is around freezing. So 266 degrees Kelvin. Once I have that information, I can find the density of these propellants at those temperatures, and that'll tell me how much space each of them takes up. And you can see overall, our tanks hold about 374 cubic meters. So that's the standard thing. Let's see what happens when we move to liquid methane. Now, 60 degrees Kelvin for the LOX, about 96 degrees Kelvin for the liquid methane. That's subchilled. If I recall right, it turns to a solid at about 90 or 92. So that's pretty much about as cold as you would want to get it. Now, the Raptor uses a different mixture ratio because the chemistry between the fuels and the oxidizer are different between Kerolox and Methalox. So that helps us a little. So we burn more LOX. We need more LOX for a given amount of fuel. But unfortunately, the liquid methane is about half the density of RP1 and even a little less than LOX. So basically, we took all the RP1, replaced it with liquid methane, but that still wasn't enough to get the mixture ratio we needed. So we had to take a little bit of the LOX tank and dedicate that to liquid methane. Now, where this really shows up, okay, do a little math here. We can see the tankage sizes if you care. We can see the weights. The part where this really shows up is the overall propellant weight goes way down. And this is not really unexpected. The liquid methane is less dense than either the RP1 or the LOX. So we just can't put as much weight in for a given volume. So once we have that, we can look through some mass data. We have the weight of an empty stage. We have how much the engines weigh. We have the payload. That's nominally what Starlink plus the fully fueled upper stage weighs. And that gives us a dry mass. And you can see that the Raptors are quite a bit heavier, but we're only using 4 of them. So the dry mass is really pretty close. Where we see the big difference is in propellant. And that means our wet mass is quite a bit different. So we went from 570 some thousand kilograms all the way down to 500. And what does that mean? Well, that pushes the mass ratio way down for the Raptors. And that simply is not good when we're looking for delta V, because the mass ratio is the wet mass divided by the dry mass. What's the effect of this? Well, the effect of this is when we go back and look at the delta V, we have 2 factors that are kind of fighting each other. So at first look, we would expect the Raptor would be a great solution because the ISP is so much higher. It's 339 for the Raptor versus a little less than 300 for the Merlin. So it's about 10% better. So we would expect a big difference in delta V. Unfortunately, because of the difference in mass ratio, we lose something. So the Merlin mass ratio, you can pack a lot of propellant into those tanks. Its mass ratio is 3.64, and the factor we end up with is 1.29. Raptor, 3.13 and 1.14, which is about 10% difference. So Raptor gains about 10% in ISP, but it loses about 10% in ratio. And that means we end up with delta V really pretty much the same, which is kind of surprising, I thought. Looking at thrust to weight, this shows the numbers directly. Interestingly, the Raptor actually has less overall thrust, but remember it has a lot less weight because the propellants are lighter. So it actually has a thrust to weight a little better than Merlin. Ends up being about 8% better. What does that mean? Well, when we have a higher thrust to weight, basically we spend less time going from the launch pad to the time that we stage. And how do you figure that out? Well, we know how much propellant there is. We know what the thrust is. And that lets us figure out something called mass flow rate. And the mass flow rate is simply how much propellant we are burning every second. And that's dependent on thrust, and that's dependent on the exhaust velocity. And ISP are really the same. If you want to go look at, want more information, go look at my link on specific impulse. So basically what that means is the Raptor is a little more fuel efficient. So we know the mass flow rate, and we can divide those two things, and we can figure out how many seconds that it takes each stage to run. And the Merlin will run for 141 seconds. The Raptor will run for 131 seconds. And we know, because they have very similar delta V, that they will end up at a very similar velocity. So basically, Merlin spends 10 seconds more fighting gravity than Raptor does. Now, that's a simplistic calculation. That's kind of assuming that you go straight up. And of course, first stages go mostly straight up, but they also go to the side a little. So that's a little off. On the other hand, it also assumes that you're running at full thrust the whole time, and we know that isn't true either. So this is probably pretty close. So basically, 10 seconds difference. Every second, you're losing about 9.8 meters per second. Fighting against gravity, so roughly 100 meters per second less gravity loss. And that really doesn't seem like a lot, but that's about 2%. And another way to look at this is 2% of delta V is roughly 6 seconds of ISP. So you can think that's a pretty big deal, and this is the reason that you really want high thrust motors, especially on a first stage. So landing, I didn't talk about in the sales pitch. Obviously, we have 4 Raptors here. That doesn't work very well for landing. And not only are they not on axis, they don't throttle down enough for you to actually probably land with one. Maybe you could. It'd be a little marginal. But I was just thinking about it. There's actually room to probably sneak a Merlin in there in the middle. Maybe you can get one with a smaller nozzle because it doesn't really have to perform very well. It's a little hard because now you have 2 fuels and you need a place to put a little bit of RP1. So I thought maybe you could put little small circular tanks in between the Raptors. And you could probably build this and it would probably work. Probably a pretty stupid idea, but I think you can do that. So this really begs the question. Why Methalox? And remember, this is a gas generator Merlin compared with a stage combustion Raptor. And we generally expect that the gas generator Merlin would lose pretty handily. But basically the whole problem here is that the mass ratio is really, really important. There's a reason why so many rockets have used gas generator RP1 engines or stage combustion RP1 engines in their first stage. It's a great, great approach. So the question is, why is SpaceX doing Methalox? And there are really 3 reasons. The first is reusability. The downside of RP1 is that it tends to not burn very clean. You end up with a lot of soot, and that's why there's so much soot on the return stages. It just doesn't burn very well. What that means is you get soot around the inside of your engine. You have to have something to deal with it. And that's just kind of unfortunate. The second is cost. And we call RP1 refined kerosene, but it's really a very specific specification. And there are only a few places in the country that make RP1. And therefore, it's not very inexpensive. It's a fairly costly fuel. And if you wanted to fly a lot more, you'd have to find someone who could make a lot more RP1. Methane, well, methane is a major component in natural gas. So it means you can get it from commercial suppliers, or you can build your own essentially gas extraction, gas refining plant that will take natural gas and give you methane out of it. So it's pretty attractive from that perspective. And the third reason, well, whenever you think about SpaceX, you always have to think about Mars. And it turns out that Methalox can actually be, at least theoretically, produced on Mars. You have carbon dioxide, assuming you can get water out of the crust. You can go through some kind of fancy chemistry, and you can create methane and store it and liquefy it. So methane is one of those fuels that you could make on Mars. And you could actually make it on the Earth too, if you wanted to. And probably be a little bit more costly than just using natural gas. But that's something you could do in the long term. So the other question is, if you're on Mars and you have water, why wouldn't you just do liquid hydrogen? And the reason you don't do liquid hydrogen is, you remember that mass ratio we were talking about? It's way, way, way worse for liquid hydrogen. So methylox is a really nice fuel in this case. Not as dense as RP1, but much better than liquid hydrogen. I wanted to include one reference here because it took me forever to find it. If you want to talk about sub-chilled propellants, like liquid oxygen, liquid hydrogen, liquid methane, you need to know what their density is, and that was not easy to find. I found this nice reference. NIST has this neat little calculator, and you go in and you say, I'm interested in this particular substance, and I want you to show me the density between these temperatures, and it'll draw you a very nice graph. So if you want to have that information, go here. Thanks. I hope you enjoyed both the sales pitch and the explanation after it. Please subscribe.